Good morning, students. Today we are going to discuss the next topic from chapter 6, and the chapter 6 is your work, energy and power. Now in our previous class we discussed work done by the constant force. Now in today we are going to discuss work done by a variable force. Now you see this figure, here we have considered y-axis as your force axis. F, capital F within bracket x, it means force is a function of x and x is your position. So variable force means what? The force which changes its magnitude with respect to the position. That is your variable force. Now on the x-axis part we have considered the displacement, and y-axis part we have considered the variable force. And the graph is your curve. It moves from lower level to higher level. Now here we have to find work done. So for that, what we have done, we have considered any 2 points on the graph, and here the 2 points are small a and small b. So what we have done, considering small a and small b, we have dropped lines parallel to the force axis as well as parallel to the displacement axis. Now if we drop line, you will see the below the curve AB you do have a triangular region as well as your rectangular region. But the triangular region is not exactly triangle, because that one is not your straight. AB is not straight, rather it is little bit curved. And A and B, if very close to each other, then you can consider that curved part as your straight line. So here we are considering A and B, any 2 points on the curve. Now if A and B are very close to each other, what happens? Basically the triangular region vanishes and you do have only the rectangular region, that is your ACDEA. So here we have written, if A and B are very close to each other, then area ABCDEA is nothing but the area ACDEA. So what happened? Basically that triangular region disappeared if we consider A and B very close to each other. Now if the area changes like this, so it is now is your rectangle, so the length axis as well as the breadth axis, if you consider AC corresponds to your force that is defined by small f with a function of x, then that gives you the height of the rectangle, and ED part, that is your delta x, gives you the breadth of the rectangle or width of the rectangle. So area of the region ACDEA is nothing but is your fx into delta x. Now fx into delta x, this is the dimension of work done, is not it? Force into displacement or magnitude of the force and distance, that is nothing but the dimension for the work done. So basically this area part ACDEA, or if A and B are very close to each other, then ABCDEA gives you the work done for the small movement, which is nothing but is your delta x, corresponding to the force small f function of x. So this is your work done for very very close 2 points A and B, which is very close to each other, and A and B is on the curve. So if A and B is very close to each other, then we have to drop line, and it seems to be the strips. Now in this way we can divide the area bounded by the curve, that is PQ, in the strips of very small width, and in each case we have to find the area, and that area gives you the work done, and if we sum up the area, then we'll get the total work done under the curve PQ. So this is the work done for a very small width delta x when A and B are very close to each other. So if you have to find the total work done, then you have to find the area, that is your PQRS, area PQRSP, area PQRSP, that is the area bounded by the curve with the distance axis or the displacement axis. Then area of sum of the area of the strips below the curve, is not it? So if you divide the region into strips considering any 2 points which are very close to each other, then in each case you have to find the work done and you have to sum up the work done. And sum of the work done means you have to find the area of the each strips and you have to sum up the area. Then you will get the total work done, and the total work done is nothing but the area bounded by the curve with the displacement axis. So that's why we have written sum of the area of the strips below the curve. These strips, I think you have understood. If A and B are very close to each other, then that triangular part vanishes and you do have rectangle, and this area triangle and rectangle together is nothing but is your strips. And if A and B are very close to each other, then triangular region vanishes, you do have only the rectangular region. So here we have written area PQRSP is nothing but the sum of the area of the strips below the curve, PQ obviously, sum of the work done for the each strips. So for each strip is nothing but the area of the each strip is nothing but the work done. So sum of the area you have to find it out, and that is nothing but is your if A and B are very close to each other, it means delta x tends to 0. That's why we have given limit delta x tends to 0, and with the sigma notation we have given fx delta x. So limit delta x tends to 0, sigma notation fx delta x. So this whole together can be defined as your integration. So integration, that line is nothing but a s. S is summation. Integration is nothing but the modified form of addition considering the limit xi xf fx dx. The delta x goes to dx. It means you are dividing the region with uniform width, strips with uniform width. So this gives you the total work done. So if someone asks you to define the work done under variable force, we have to go for the integration formula, that is xi to xf, that is starting, xi is your initial, xf is your final, fx dx. That is your total work done. Now as we have to use this formula, that's why we must have to know these two basic formula of integration, that is your x to the power n dx, x to the power n plus 1 by n plus 1 plus constant, if it is indefinite integral. If it is definite integral like this, definite in the sense if you know the starting and ending point, then it is your definite integral, and in that case you have not to write constant, it's only the formula, and integration of dx is your x plus constant. In indefinite integral we have to go for the constant of integration, and this is your formula for the work done by the variable force. Now here we are going to define this formula by considering this numerical. A particle is moving along x-axis from x equal to 0 to x equal to 4 meter under the action of the force given by F equal to 5 minus 7x plus 4x square Newton. What will be the work done in this process? So this formula we have to define xi xf fx dx. So fx is nothing but is a capital F, that is your 5 minus 7x plus 4x square, and dx is already there. Now you have to split up, so 0 to 4, 5 is your constant, so it comes out from the integration symbol dx, and 7 comes out x dx, 4 comes out x square dx. This symbol is nothing but is your s. S is for summation. If you stretch the end, it becomes your symbol of integration. So integration of dx, already you have written here, dx is your x, so x third bracket 0 to 4, that is your limit, and minus 7 x dx, we are going to use this formula, x to the power n is your 1, so x square by 2, so x square by 2 integration third bracket 0 to 4, minus 4, again n is your 2, so x3 by 3 0 to 4, so upper limit minus lower limit 5, 4 minus 0, minus 7, 4 square is your 16 by 2 minus 0, plus 4, 64 by 3 minus 0. So 20 minus 2, 16 goes of 80, 8, 8, 7, 56, 20 minus 56 plus 256 by 3. So minus 36, and this is your 85.3. So it comes out to your 49.3 joule. So this is the formula you have to use to define work done by the variable force. You have to go for the integration. Integration you will get in class 12, but in physics you must have to know before that. So what formula we are going to use we will give simultaneously. So it's a very simple, just check it out, this formula. Now next we are going to define kinetic energy, because the chapter is your work energy and power. So energy is nothing but the work done, is not it? So the energy possessed by a body by virtue of its motion is called as kinetic energy. Now in physics you must have to go for the expression rather than the statement, and wherever statement required, write it in brief. So number 1, dw f dx. What does it define? Small work done when force and displacement are in same direction. So F equal to ma, already we have defined in our previous chapter. Ma is your acceleration dv dt. So dw equal to m dv dt dx. So just arrange it, m dx dt, dx by dt. When I say dx dt, you must have to understand that it is your dx by dt. Okay, so in differentiation it is used to say like that, m dx by dt into dv. So dx dt is your v, that is your velocity. Now we have to integrate considering the limit 0 to w and the limit initial to final velocity. So dw is your w, and with the limit 0 to w minus or equal m, that is your v dv, exponent is your 1, so v square by 2 u to v. So upper limit minus lower limit, w minus 0 m, v square by 2 minus u square by 2. So w equal to m v square by 2 minus u square by 2. That is your work done equal to change in kinetic energy. This is your work energy principle. So if someone asks you to define the work energy principle, then you can define up to this much. But if someone asks you for the kinetic energy, then you have to use this limitation. That is, if u equal to 0, then kinetic energy equal to work done. Because you see, if the object initially at rest and if you do work, then the energy you have spent for the work done goes to the kinetic energy of the object, is not it? So that's why you can say that if u equal to 0, then kinetic energy is equal to work done, w equal to is your half m v square. So please go through and try to find out your doubts. As we are moving, we are getting tougher. So please go through this part and try to find out your doubt. So this is all about. Thank you.